Let's talk a little bit about the use of differential scanning calorimetry to monitor phase transitions. Now, what a differential scanning calorimeter does, maybe we'll say a little bit about on the next slide, how it operates, but what we can say from the chemical potential of a system. Now remember, the more stable phase has the lowest chemical potential, and so if you have a transition from one phase to another, you should have a line representing how the chemical potential changes with temperature. Now, if you do these experiments as we normally do in a laboratory at constant pressure, the change in chemical potential with temperature should be equal to negative of the molar enthalpy of the process. So if we look at this, now if d mu dt is equal to S, I can claim I have d mu f dt equal to SF molar, and d mu I dt equal to minus SI molar. And then if I take the difference between those chemical potentials, as I show in the middle of the slide here, the change in delta mu with respect to T at fixed P will be equal to the change in the molar entropy of transition, delta S transition over T. Okay, so then if I realize that the change in molar entropy of transition is equal to the molar enthalpy of transition over the transition temperature, what I can do is recognize that the differential scanning calorimeter, if it tracks these values, will have a so-called discontinuity when you have a phase transition. Now, what do we mean by a discontinuity? We mean the curve is no longer smooth. So when you have a discontinuity, there's a change in the slope of the curve from one part of the curve to another. So when I have this bent over curve, you see if I extrapolate them with some straight lines added to them, that is an indication of where the chemical potentials of these two phases of the same material are crossing. Now, if I were to monitor this from the enthalpy of the material versus temperature, what I would see is the enthalpy is going to undergo some sort of change as I change the temperature, and then at the transition point, there will be a discontinuity in the enthalpy curve. Now notice this is a discontinuity in the curve itself. In the mu versus t, it's a discontinuity in the slope of the curve. In the h versus t, it's a discontinuity in the curve itself. It literally changes from one line to another line when I hit the temperature of that transition. Now, a differential scanning calorimeter can be useful to monitor such things. So maybe on the next slide, we'll say a little bit more about how this differential scanning calorimeter operates. Here I have a little cartoon of a schematic of the setup of a differential scanning calorimeter. What it contains is a pretty good heating element that can take materials from their solid metals and typical things, melt them all the way through their liquid transition points, which very frequently needs to be fairly high falutin heating elements to do such. Then what you do is you put your sample in a crucible, and you also put another empty crucible in the reference chamber, much like you might do in spectroscopy, kind of doing the same thing here. Then you have a computer deliver the same heat to both the reference and the sample, and you note what kind of differences occur. That's where you get the idea of this differential scanning calorimetry. Calorimetry comes about when we're monitoring the change in the properties of the heat capacity or other properties. When we add heat, how does the temperature of the system change? That's what calorimetry does. You input heat and you monitor how the temperature changes with that input heat. So this is just a fancy way of doing such things. So how does the scanning calorimeter do this? It monitors the power and the temperature change with time that the system undergoes. So power, of course, is an electrical quantity. The definition of power is energy per unit time. So I can measure the energy by how the inner workings of this thing deliver through coils in the heating element to the individual crucibles, both the reference and the sample. So power is energy over time. I can monitor that as heat over time. And if I'm working at constant pressure, as I said we were doing on the previous slide, the heat at constant pressure is the enthalpy, and the change in enthalpy as that heat is added with time. And of course, the heat at constant pressure is C sub P delta T with time. So all these relationships are monitored by the computer. Of course, it's going to measure the watts of power that it's putting into the heating element, and that is directly relatable to either delta H over T or C sub P delta T over T. Now, as I said, it also monitors the heating rate, and the heating rate is, I'm giving here the symbol rho, and that's the change in temperature. So it has some thermometer, so some thermistor to not only monitor how much heat it's putting in, but to monitor the change in temperature that both the reference and the sample are undergoing as you add this heat into it. So this heating rate, rho, is defined as the change in temperature with time. And then, of course, with the wizardry of the computer, it can divide the power input by the heating rate. And you can see in various forms that would either be Q over delta T by just substituting the two expressions above, or it would be delta H over delta T to give us a graph like we saw on the previous slide, or finally, it would just simply be equal to C sub P. So the heat capacity of the material can be directly determined by the ratio of the power supplied through the heating elements divided by the so-called heating rate, or change in temperature with time that the sample undergoes. Now, very interestingly, if you look at a plot of the heat capacity with time, what you'll generally see is some gradual increase of it when it is in a particular phase, and then the heat capacity goes infinite at the transition temperature. So it just spikes up off the chart at the transition temperature. After the entire sample has melted, then the heat capacity curve will settle back down, and then again, as you increase the temperature past the transition temperature, there will be typically a gradual increase in the heat capacity of the material as temperature increases. So let's mention a few words about that infinite transition at the or infinite form of the heat capacity at the transition temperature. That's a very interesting phenomenon, which is stating that what is going to go on there is that the sample will no longer heat when you come to the transition temperature. Now, let's think of a familiar case where you may observe this occurrence. Put some water on the stove, and as you put heat energy into the water on the stove, the temperature changes. So you can monitor a rho as delta T over T at that particular point. Now, what happens though when the water begins to boil? The temperature no longer begins to rise. So delta T goes to 0 when the water begins to be boiling. Now you're still putting heat in to the sample, but delta T has gone to 0, and so if you divide, let's think of this as Q equals C sub P delta T. At the transition temperature, you no longer have a change in temperature. Delta T goes to 0, and so C sub P is Q over delta T. C sub P goes to infinity at the transition temperature. So think of it another way. You no longer are experiencing a change in temperature, yet you are dumping in heat. According to the equation Q equals C sub P delta T, there should be a change in temperature unless Q over Cp is 0. And Q over Cp can be 0 if Cp is infinite. So when a transition temperature, you reach the transition temperature, the heat capacity becomes infinite so that the temperature remains the same while the sample is changing phase. As soon as the complete sample has changed phase, now the sample in the new phase can increase in temperature. So we often call this a lambda transition of the heat capacity. When you hit the transition temperature, you get this spike that kind of looks like a lambda in a way from the Greek letters. So this has been often referred to as a lambda transition. Some materials undergo what is known as a second order phase transition. And in a second order phase transition, if you were to make a plot with, again, with a differential scanning calorimeter of chemical potential with temperature, when you come to the phase transition, instead of being discontinuous, now remember what that means is the lines kind of bend and the slope becomes discontinuous. Here they have a change so that there is a 0 slope at the transition temperature, but not a discontinuity. It's not a jagged point in the mu versus T plot. It's just a change in inflection of the chemical potential curve with temperature when we have what we call the so-called second order phase transition. Now, if I were to plot H versus T for the second order phase transition, instead of being a discontinuous curve, refer back to my first order phase transition, what I would see here is a jump in the curve of the type that we're seeing here. Again, I'm getting a discontinuous slope, but I'm not getting two separate curves for the enthalpy versus temperature. Now, the other thing is we saw for the first order phase transition, what would happen if you plotted the heat capacity versus temperature. You got an infinite heat capacity at the transition temperature. Here what you will note is a dramatic rise in the heat capacity, but it doesn't go infinite at the transition temperature, and then it pops down when the complete sample has changed phase, and you have just a more normal gradual increase in the constant pressure heat capacity in this new phase. Now, if you look again at this CP versus T curve, this looks much more like a lambda, and this is again what Ehrenfest originally classified as a second order phase transition, when you have this curve that looks like a lambda, and in particular for the second order one, the CCP doesn't go infinite. It does look a lot more like a lambda transition of the so-called of the constant pressure heat capacity. what we can think of for chemical potential, since it is the change in the Gibbs energy with respect to the moles of change in composition of a particular component, we can think of it as what is known as a partial molar quantity. Now what we can do is we can describe other mechanical measured values other than energetic measured values. We can describe them by partial molar quantities as well. For instance, the infinitesimal volume of individual components of a mixture, now I stayed here for a binary mixture, but it could be as many components as I wish, but we'll start by monitoring it for a binary mixture or a mixture of two components. I can define the partial molar quantity, known as the partial molar volume of the solution, much like I did for this partial molar Gibbs function that I called the chemical potential. So I'm going to define for component A a quantity VA such that it is how V, or the volume of the system, changes with change in N at constant pressure, temperature, and moles of the other quantity. Okay, so I have a mixture of A and B. So while I hold the moles of B fixed, I look at how the volume of the solution varies with respect to change in the moles of A, change in composition of A, at constant pressure and temperature. Now again, I really could change those variables, pressure and temperature. I could measure them at pressure and volume and temperature. Or I could measure them at entropy and volume if I wanted to use the form of the chemical potential from the internal energy. But the Gibbs free energy is our most commonly employed form because of its connection with P and T. So I'm going to define this VA to be dV dNA at fixed P, T, and NB. Then what I can think of, since volume, of course, is an exact differential, and since this volume is going to be a function of the number of moles of A and moles of B I mix, so V is a function of NA and NB, I can do just like I've been doing all along here and state that the exact differential of volume will be how the volume changes with NA times the increment of change in NA plus how the volume changes with NB times the increment of change in NB. We've done this many times over, particularly though up to this point we did it with energetic functions. Now I'm doing it with measurable parameters of a sample. Here in this instance, I'm doing it with the volume. Now from the definition above, I see that this, what I can do is I can take the increment of change of the volume dV to be equal to VA and dNA plus VB dNB when I compare the definition of VA above and make a similar definition for VB. I note that dV is equal to VA dNA plus VB dNB. Let's consider the situation where I monitor the volume of a binary mixture. I'm going to mix A with B. Let's say I'm mixing two miscible liquids, and that's probably the easiest thing to envision. I'm going to mix two miscible liquids, meaning they make solution in any proportion. And I'm going to monitor, I'm going to put some fixed amount of B in, and I'm going to vary the amount of A I add, and I'm going to monitor how the volume varies as I dump A into the fixed amount of B. So I make a plot of this, and you'll note I give some representative form of what this might look like. And let's consider it now in terms of what I mean by this quantity, the partial molar volume. Notice at the beginning when I'm adding Na, there's a large region of very nice linearity to the slope of the curve. So what it's saying in that constant positive area where I'm having a nice straight line is that the slope is constant. Now, what does it mean that the slope is constant? That means that dV dNA is a fixed value over that range. So what that would mean is that VA is not changing with NA. Now, if I did a similar plot of how A is being held constant while I dump in only the B, and I can identify a similar region of behavior of a straight section of the curve where I have then how the slope of this would now be a function of the change in volume with NB, I could claim in a region like that that VB is constant over the range of addition of B, of moles of B at that particular point. So then if I were to integrate dV from 0, as you see, I start with 0 volume, so I'll start that integration at 0, and I'll of course start my moles of A and moles of B at 0 moles when I'm at 0 volume. Then because there's linearity of the volume function of the moles added over these ranges, I can pull the partial molar volume out during those ranges, and I can just integrate over the change in moles dNA and dNB, and learn that since the limits of these are from no added material up to some final value NA and NB, that the volume is simply equal to the partial molar volume times the moles of NA, partial molar volume of A, times the moles of NA, plus the partial molar volume of B times the moles of NB. Now, if you are in regimes where you are not having a straight line of this function, if it's curving in any way, then that's telling you that dV dNA or dV dNB is not constant, and it is actually a function of the amount of moles present, and you can't pull it out of the integral that you see listed there. And you would have to have maybe some curve fit. What you do in a case like that is you fit the curve to a polynomial. So you have a polynomial in n fit of the curve, literally taking the differential of the polynomial fit of the curve, and you could then evaluate. So VA would be a function of n as a polynomial fit. You put it in that polynomial fit into this integral and integrate that expression to give you what the particular volume would be at given numbers of moles of NA and NB. These are the kinds of tricks, just like actually the DSC trick, these are the kind of things that get explored in the PChem lab section that accompanies this, but no one seems to want to take the PChem lab part, but that's another story for another time. But that's the kind of things we would explore in there. Now, another thing you should notice, let's go back to the curve. We note that there's the particular curve I drew, there's an inflection point where the slope of the function is 0. That means that dV dNA is 0 at that point. That would mean at a point like that, we are saying that there is 0 partial molar volume of the solution at that point. Then I have the curve heading downward. There's negative slope of the partial molar volume. So actually, you can have negative partial molar volumes depending on the way things are mixed. Okay, now where do you see curves like this that occur in miscible mixtures of components such as water with ethanol? Water and ethanol are miscible. They mix in any proportion you want. However, the sum of their individual volumes does not equal the total volume of the solution. They have intermolecular forces which allow them to feel each other the same, but the way they pack, because ethanol has the big C2H5 tail on it, water molecules can kind of tuck in up among the individual ethanol molecules depending on the ratio and proportion of ethanol to water. So when you mix ethanol with water, say you mix 10 mils of ethanol with 8 mils of water, you're not guaranteed to get 18 mils of solution due to the difference in packing between the water molecules relative to the ethanol molecules. Now again, things of this can be explored, and the tool that we use to explore things like this are partial molar volumes of each component when mixed together and placed in various proportions in solution. Okay, so what we learned on the previous slide was when there was constant slope of these curves, so that dV, dNA, and dV, dNB are constant, you could pull them out and integrate the equation and get that the volume was just VA-NA plus VB-NB. But what happens in the regions where the partial molar volumes are varying, or where these curves look like they're having inflections, or when these curves look actually like curves instead of like straight lines? Anytime there's curvature, that is indication that the partial molar quantity is not constant, it is changing. And as I show there tangentially, you can get a point slope at that infinitesimal, but generally speaking, the partial molar volume is changing. So in a case like that, since V is equal to VA-NA plus VB-NB, then the increment of change dV must be VA-dNA plus NA-dVA plus VB-dNB plus NB-dVB. I use the product rule on the form of how the volume behaves. But since volume is a state function, that means independent of the path, you have to get the same value of the volume, whether or not there is variation or not. So that means that the dV equals VA dNA plus VB dNB must also be true if the partial molar volumes are varying. Interestingly, then, what that says is that the cross terms must be canceling. Compare the second equation to the third equation, and that says that the NAdVA term plus the NBdVB term must equal 0. Now, they don't individually equal 0, but their sum must equal 0. And that very interesting result says that if I look at how the volume of A is varying, it would be equal to minus NB over NA times dVB. So remember what VA is. That's the partial molar volume of A. And here's what this is saying. In a region where the partial molar volume of A is varying positively, simultaneously the partial molar volume of B must be varying in the opposite sense, or must be varying negatively. So when one is varying positively, the other is varying negatively. Now remember, if they are constant, then dVA is 0 and dVB is 0. So that equation, those two terms still cancel in the positive, or in the constant partial molar volume cases. But when there isn't a constant partial molar volume, as the curve above demonstrates, that is a plot of how VA varies with NA, or that's a plot of how V varies with NA. You'd have to also look at a plot of how V varies with NB, and you would note that in that regime where I'm seeing negative partial molar volume of A, I would be having positive partial molar volume of B in that exact same regime. That statement has been verified and proven. Again, the mathematical complexity of this has been investigated and has been shown to be true. Now what we can do is make the same argument. Instead of now to a measurable quantity like volume, let's make the argument to the chemical potential itself. Well, again, what we're going to choose is the chemical potential in the form from the Gibbs function because of the utility of its constant pressure and temperature definition, much like we use in a laboratory. So mu A is dGdNA at fixed PT and NB in a binary mixture. So, according to the first and second law combination, the fundamental equation for change in composition, the increment of change dG would be VdP minus SdT plus mu A dNA plus mu B dNB. We've discussed that several times over now. And if we specify constant temperature and pressure, then the increment of change in the Gibbs energy will just be mu A dNA plus mu B dNB. Now again, because G is a state function, even if mu A and mu B vary with varying composition, so there are points where mu A and mu B are varying, as we talked about on the previous slide, so that in general, if I were to integrate this expression, I would get that G equals mu A NA plus mu B NB. That would be the general expression for the behavior of G, just like it was the general expression for the behavior of V, but the argument first comes from the fact that that is the general behavior of the expression only if mu A is constant and mu B is constant, just like previously the argument was only if VA was constant and VB is constant, can you make the statement that dG equals mu A dNA plus mu B dNB. Well, what that is implying then is in regimes where mu A is not constant, where it's varying with some curvature with respect to NA and NB, that NA d mu A plus NB d mu B must equal 0. That has to be a true statement in order for that statement above to hold. So just like we did for the partial molar volume, if I rearrange and solve for the increment of change in chemical potential A, I would have that that's equal to NB over NA times the increment of change of the chemical potential of B. So in other words, when the chemical potential of one material is increasing with composition, simultaneously the chemical potential of the other component of the binary mixture must be decreasing with composition at that same time. Now, if you have more than a binary mixture, you have a multiple component system, then you get in general that the sum over J of Nj d mu J is 0. So all terms together have to sum to 0. This is known as the Gibbs-Duhem equation and was discussed at great length. I told you Gibbs was all over this chemical potential quantity and all over this form of thermodynamic energy in the 1800s and described this very succinctly for mixtures of components. Let's look at how we can model the chemical potential of an ideal gas. We're going to begin with the fact that according to the fundamental equation and the exact differential properties that we've seen many times over, that dGdP at fixed T is equal to the volume of the sample. If I now go to the case that I have a pure sample, then Gm, the molar Gibbs function, is proportional or is exactly the chemical potential of that pure sample. So then d mu dP at fixed T is equal to the molar volume of the sample. And if I then just take the dP to both sides of this equation and just state that I'm going to do this isothermally, then the increment of change in the chemical potential will be Vm times the increment of change of the pressure. And if I substitute for the ideal gas, that Vm is RT over P, and I know that R and T are constant at this isothermal process, I get that the chemical potential at the final temperature or final conditions of pressure minus the chemical potential at the initial pressure conditions must be equal to RT ln PF over PI. Now, if I move the chemical potential at the initial pressure over to the other side and claim that that's at the standard ambient pressure of 1 bar, so I'm going to use 1 bar as PI in both cases, then mu I is simply mu 0, which is the molar Gibbs energy of that, the molar Gibbs energy of formation of the material. So if I know the Gibbs energy of formation of a gas, say argon, whatever I want, I can just substitute it in here for mu 0, then treating the argon as a ideal gas, I can get the chemical potential of that ideal gas at any other pressure I would desire from this relationship that we show here. Now let's look at the change in the Gibbs energy as you mix two gases that are behaving ideally. So the chamber you see above there, I have a separation, something between two ideal gases A and B. I know the number of moles of A, and I know that it is at some pressure P. I know on the other side the moles of B, and I'm going to claim it's at the same pressure P as gas A, and it is also at the same temperature T. So P and T are common to the two gases on either side of the partition, but I'm not specifying that the number of moles of A and B must be the same. So let's calculate the initial Gibbs energy of the gas, and we're going to use the formula from the previous slide that says, because of the Gibbs-Duhem thing we talked about, that GA must be mu A NA plus mu B NB, and for mu A and mu B, I'm going to substitute the formula that we found at the end of the previous slide, that mu A is equal to mu A0, that is the what I get from delta G of formation, plus RT ln P over P0. So this P0, remember, is the standard ambient pressure. If mu A is the standard ambient Gibbs energy of formation, that's what I have to use for that on the bottom there. And so I just sum those two terms. I can calculate a GF in a very similar fashion. So underneath the second box there, you see GF. It's again going to be NaUAF, if you like, plus NBUBF, if you like. And how do I calculate UBF? Let's notice after I mix the gases, they remain isothermal. The temperature in the mixed box is the same as the separated temperatures in the above box. The pressure in the mixed box is the same as it was in the separated box, but now notice PA and PB are going to be values lower than P itself, because of course the ideal gases are going to mix until their partial pressures equal the total pressure. As NA expands into the entire chamber, PA is less than P. As NB expands into the entire chamber, PB is less than P, but we are guaranteed that the sum of those partial pressures, when they spread throughout the chamber, would be the same as the initial pressure of the separated gases in the chamber, because they're ideal gases, and they really don't feel each other any differently than they feel themselves, because ideal gases have only kinetic energy, there's no potential energy, so the pressure they exert in the mixed chamber is going to be the same as they separately exerted in the smaller chambers. However, the partial pressures of each are going to adjust so that the sum of them now gives me that final pressure. Now, delta G of mixture, I'll claim, is GF minus GI, and I can find GF minus GI by subtracting the two expressions you see above, and you will see that the molar Gibbs energies of formation are going to cancel in the expressions above and below, and by playing little games with natural logarithms, the natural logarithm of the P0 values are going to cancel in the expressions above and below, so that the delta G of mix will be NART ln PA over P plus NART ln PB over P, the original pressure. I can change the form and express the free energy of mixing of ideal gases in terms of the mole fractions of the gases instead of the partial pressures of the gases, if I note that, of course, from the definition of mole fraction, it is for mole fraction of A, it's Na over N tote. Now, if I write Na as being equal to PAV over RT, and I write N tote as being equal to P tote V over RT, since V, R, and T are the same in those two expressions, they will divide out, and XA, which is NA over N tote by definition, is also equal to PA over P tote. This is where the little formula comes about, that the partial pressure of A is equal to XA times P tote. You can rearrange that and get that as well if you'd like. Now, XB can be done in the same way. XB is defined as NB over N total, and NB from the ideal gas formula is RT over, it's PV over RT, or I'm sorry, that'd be, in that case, it'd be PBV over RT for NB, and for N tote, it'd be P tote V over RT. So if I divide NB by N tote, the V, R, and T's will cancel, and XB can either be written as NB over N tote or PB over P tote. Now, I'm going to substitute into the very top equation the fact that if I want to multiply through by N tote over N tote, then I'll have NA over N tote times N tote, which is N tote times XA in the first term. Then I'll have NB times N tote over N tote in the second term by multiplying through by N tote over N tote. And that gives me N tote times XB in the second term. And also, if I put the PA over P tote is equal to XA and PB over P tote is equal to XB, I can simplify the delta G of mixing to eliminate the pressures and express it only in terms of how many moles of each gas I'm mixing as being the enthalpy, or I'm sorry, the free energy of mixing two ideal gases is N tote RT times XA ln XA plus XB ln XB. Now guess what? If I were to extend this to mixing three gases, I would be N tote RT times three terms. There would be a third term in that parentheses, XC ln XC. This is the only difference that would come about. Now I can easily get other thermodynamic quantities of mixing, because by noting from the original behavior of G that dG dt at fixed P and NA and NB would be equal to minus S. So that would be the molar entropy of the situation. And if I now say that dGF would be minus SF, put into that expression, dGI would be minus SI, do those two subtractions, I can find delta S mix by taking the derivative of delta G mix with respect to T. So it is equal to N tote R XA ln XA plus XB ln XB. Now, because delta G equals delta H minus T delta S, and then I rearrange that and get that delta H is delta G plus T delta S, and I multiply my delta S by T and add it to delta G, I find the enthalpy of mixing ideal gases is 0. Now this should make sense to you because any enthalpy process, which is heat at constant temperature, any constant temperature process should have a zero change in enthalpy for the behavior of that process. Now notice it doesn't have a zero change in free energy. That's mainly because of the entropy term. There's going to be an increase in entropy, of course, when you mix the gases. Let's think a little bit about that. Notice, of course, XA is a fraction, XB is a fraction, so ln of XA is negative, ln of XB is negative, and then when you take that times the negative sign in front, I'm going to get a positive value for the entropy of mixing, as you would expect. I'm going to increase the randomization by mixing these gases together. But what I'm claiming, though, is that that is the source of the negative value of delta G. Notice delta G mixing should be negative. Why? Because, again, XB is negative, logarithm of XB is negative, logarithm of XA is negative, and there's no minus sign outside. So delta G mixing is going to be negative, saying it's spontaneous. Delta S mixing is going to be positive, saying it's spontaneous. And the entire source of any free energy of mixing is due to the entropy contribution of gain that you get upon mixing. There is no enthalpy change upon mixing the ideal gases. Let's look at how we can use some cleverness, a little trick, and not only monitor the chemical potential of behavior of vapors or gases, let's look at how we can monitor chemical potential in a liquid sample. And in particular, we'll begin with what we call ideal solutions. Ideal solutions are volatile mixtures of components that are low polarity. So they're things like benzene, things like hexanol, hexane, which are that are highly volatile liquids, but they're non-polar liquids as well. They stink when you open up the jar, and but they still are liquids. They have enough dispersion force to stick together well enough to be liquids, but they're very non-polar, so they don't stick to each other. They have negligible intermolecular force exerted amongst each other when they're in the liquid phase. So here's what we're going to do. We're going to take the chemical potential when they're in equilibrium. So we're going to take the phases in equilibrium, so that if I have pure A, its chemical potential in the liquid phase is in equilibrium or equal to the chemical potential of A in the vapor phase. Now, the reason we want to do a trick like this is we know how to model vapors very effectively. Gas models are very well established. So I can make a simple model of the gas. In particular, if I employ the ideal gas model of the vapor, then I am in business because I can state that the vapor in equilibrium with the liquid must have the same chemical potential. So I can now monitor the chemical potential of the liquid from its vapor. So, drawing from the previous slide then, if the chemical potential of the pure liquid is equal to the chemical potential of the pure vapor in equilibrium above it, then it will be equal to mu A0 of the vapor plus RT ln PA star, which is the vapor pressure of the liquid at temperature T. Let's be very clear about that. PA star is the vapor pressure of liquid A at temperature T. So now what I can do is I can state that because these chemical potentials in the mixture, when I mix them, okay, I'm now going to mix them, and in the mixture I have a new chemical potential of the mixture present, and mu A liquid will be equal to mu A gas 0 plus RT ln PA over P0. So PA is the vapor pressure above the mixture of liquids. Now the vapor pressure above a mixture of liquids is different than the vapor pressure of the pure sample. Okay, now when you mix components, the vapor pressure is lowered by mixing components. There's a natural vapor pressure lowering that goes on when you mix volatile components. Why? Because there's more entropy gained upon mixing, so that you don't need as much entropy present due to the sample in the vapor phase. So less of the vapor is present when you mix than there is when you don't mix. All right, so then I can eliminate the vapor pressure or the chemical potential of the pure vapor mu A0 by rearranging the equation and solving for mu A star. And when I do so, I get that mu A of the vapor is equal to the chemical potential of the pure liquid minus RT ln of PA star divided by P0. So when I substitute that expression for the chemical potential of the pure vapor into the expression on the second line, I get that the chemical potential of a liquid is equal to the chemical potential of the pure liquid plus RT ln. Now I have PA of the vapor pressure in the mixture divided by PA star, the vapor pressure in the pure sample. So here's our expression for the chemical potential of the one component of the binary liquid that we are writing as a function of the vapor above that in the form that you see here. Now, what was discovered by Francois Raoult in the 1800s was that you can express for an ideal liquid and a binary, or even doesn't matter if it's binary, trinary, whatever, a mixture of ideal liquids with low polarity and low intermolecular force that have reasonable vapor pressures that they exert, that the vapor pressure above the solution, PA, is a function of the mole fraction of the solutions in A times PA star. So if XA is equal to 0, then of course there's no A present, PA is 0. And as XA, the mole fraction, goes up to 1, PA becomes PA star. So there's a linear relationship between the vapor pressure of a component A above a solution, mixture of A and B, and the mole fraction of A in that. And of course, since XA plus XB equals 1, I could oppositely plot that PB equals XB PB star on another axis, as you can see on the plot below. And it goes from, if I'm plotting against mole fraction A from 0 to 1, then the mole fraction of B would run from 1 to 0 in the complete opposite sense, as XA runs from 0 to 1. And when XA equals 1, that means that XB equals 0 and PB equals 0. And then when I get down to XA equals 0, that of course means XB equals 1. And when XB equals 1, PB would equal PB star on that graph. So there's a nice linear relationship between the variation of PB with mole fraction as well as there is for PA with mole fraction. Now, of course, at all times, the sum of PA, the sum of the vapor pressures total above the solution must be equal to PA plus PB, and that must run from the vapor pressure of pure B when there is no A present down to the vapor pressure of pure A when there's no B present. You can tell from this plot that A is a less volatile material than B because the vapor pressure of pure A is greater than for pure B. I'm sorry, the vapor pressure of pure B, is greater than it is for pure A. Now, if Raoult's law is placed into the expression for the chemical potential, we find that the chemical potential of liquid A is equal to the chemical potential of pure A, not in the mixture, and of course that can be found from the delta G of formation of liquid A. That's where I can get that value. Mu A star comes from the delta G of formation of liquid A, and then I just add to that RT ln of XA, mole fraction of A in the mixture of components. Now the equation we found on the previous slide for Raoult's law holds only in the case of what we called, again, the ideal solution. What is the idea of the ideal solution? It's kind of like the idea of the ideal gas. The particles don't feel each other in the ideal gas. And in the ideal solution, the particles don't feel each other either. So when we mix ideal gases, there's no change in properties of the mixture compared to the separated, because the mixture doesn't feel A to B, but they didn't feel A to A or B to B either. So the relationships between the mixture and the separated components are such that you have these linear behaviors with mole fraction. The change in partial pressure of A is strictly with an ideal gas XA times PA of the pure substance. What I'm claiming is for the ideal solution that we can get away with that less and less, because as soon as we start to have interactions between the A and B substances that we're mixing together, then that's going to cause deviations from the nice straight lines. So I'm showing two plots of Raoult's law behavior here. It's really the same thing that I saw on the previous slide. I'm mixing A and B. I'm plotting the vapor pressure above the solution as a function of mole fraction of A. And of course, mole fraction of A runs from 0 to 1. Well, that means, of course, that mole fraction of B runs opposite of that. It runs from 1 to 0 on that curve. And there's a straight dashed line going from 0 to PA star, and a straight dash line going from 1 to PB star, indicating that that would be what the ideal behavior of the solutions, where PA equals XA PA star, or PB equals XB PB star. They would follow right along those dashed lines. Now, if the mixture is such that A-B interactions are favored over AA or BB interactions, so the molecules are sticky relative to one another, what that means is you will have significant lowering of the vapor pressures below the ideal forms. So notice that when the interactions between A and B are favored compared to separate A or separate B, that I experience deviation below the dashed lines because vapor pressures are lowered due to the increased stickiness that the mixture molecules feel compared to the separated molecules. Now let's compare that to the appearance of the curve on the right. On the right-hand curve, once again, the dashed lines indicate ideal behaviors. But now what I'm seeing is in this curve, there is weak interaction AB compared to AA or BB. A and B don't like each other. When A and B don't like each other, they don't stick as well together in solution, so vapor pressures are enhanced when you mix binary mixtures of A and B. So you'll note that the deviations from the dash curves on the right show vapor pressures of A, vapor pressures of B, and of course total vapor pressures summing A and B are going to be greater than they would be in the ideal solution. Let's say a few things about the limiting behavior of mixtures in real solutions, where we expect deviation from ideal behavior. Notice again, I'm showing a plot here in the middle of the page. The top is just showing the basic ideal form of Raoult's law, but the plot is showing the deviation. Of course, this is a deviation of negative nature, meaning I'm lowering vapor pressure of the components and the total vapor pressure from the ideal values. And again, this is an indication that the molecules are stickier relative to one another than they are to themselves, so that the strong intermolecular force AB is greater than AA or BB, so the vapor pressure of mixtures is lowered compared to what they would be in an ideal case. But notice what actually happens in the limit that XA approaches 1. In the limit that XA approaches 1, notice that the blue curve bends to match, eventually it must be PA star. So when XA becomes 1, PA does definitely equal PA star, whether the solution is ideal or real. So what you find is that there's a regime near where XA equals 1 where the solution is behaving ideally. The blue curve is right on the dashed curve, right up around the points where XA is 1. So where XA approaches 1, then Raoult's law is valid. PA is equal to XA PA star at those points. Now let's follow the red curve. Now really we're going in the opposite sense. We're going down to XA equals 0. So where XB approaches 1, or where XA approaches 0, the red curve starts to match along the dashed curve again as well. So at that limiting case, in that very low regime of small XA component or large XB component, then Raoult's law holds PA or PB equals XB PB. Now, at the other end of the expressions, though, it's not good. Notice down where XA is equal to 0, PA is very far deviating from the dashed line. Notice at the point where XB approaches 0, and that's of course where XA approaches 1, then PB is showing great, very, very strong deviation from the dash curve. So what was done by the fellow in the upper right-hand corner, William Henry, was he extrapolated those curves, meaning he drew a straight line extrapolating as XA approaches 0, then the expression starts to follow what's known as Henry's law, where PA equals XA KA, not PA equals XA PA 0, some value extrapolated known as KA, the Henry's law constant. Now notice where that comes out. Follow an extrapolation line that fits along the point where A is at where A is going to 0. XA is going to 0. I have an extrapolation of KA, and along that section there, PA matches XA KA. Same thing is true on the opposite curve. Look, we have big deviation where XA is 1 on the PB curve. The dashed line, the real solution is far away from it. But if I do an extrapolation that is nearly linear when XB is very small, I hit the axis over there not at PB star, but at some value I'm going to call KB. And I claim that at that extrapolation, we have PB equals XB KB for those small very tiny values of xb. So in those regimes, you can do these extrapolations and replace in the expression above, instead of using PA over PA star, I use PA over KA, or for the B expression, I would use PB over KB in those expressions above. Let's look at one of Gibbs's many signature achievements, and that is the very simple yet very powerful phase rule. Now, Gibbs's phase rule reads, as you see in the equation there, that F equals C minus P plus 2. So let's analyze what this phase rule is saying. First of all, what is F? F is the number of degrees of freedom in a system. Now, what do we mean by degrees of freedom? We mean the number of controllable parameters. Now, what do we mean by that? Well, what kind of things can we control when we make mixtures? Well, we can control how many things are placed in the mixture. And when we control how many things are, what does that correspond to? That corresponds to the number of components. The number of components is how many things I'm mixing together. But now when I do that, I can control the moles of A and the moles of B that go into the mixture of components. Okay, so if I'm putting multiple components in there, one of the things I can control would say be the mole fraction of A compared to the mole fraction of B, and so forth. Now, what are other things that I can control? Well, the pressure that I exert, or the vapor pressure that the components exert when they're mixed. The temperature. If I change the temperature, I might change the vapor pressure. Or if there's no degrees of freedom left, say I only have 1 degree of freedom, then things become fixed. Like what? The temperature at which that system can exist when you mix it in certain proportions, or the vapor pressure that it exerts at a given temperature. That's probably a little more common way of thinking about it, because that's something that we're more familiar with. So this phase rule turns out to be very simple, and there is various phases that are possible, meaning liquid phase, gas phase, solid phase. Now, you have to be a little careful when you say these things, because the vapor or gas phase are often used, but remember, there can also be, in the solid or the liquid, multiple phases, as we will maybe show some examples on the next slide. So you have to be a little careful. So liquid, solid, and gas are some states that we have for matter, yes, but we often very commonly refer to them as phases as well. So let's make some differentiation between what we mean by a phase and a state. State, again, very familiar to us, liquid, solid, gas. So let's make sure we're clear what we mean by phase. Now, one more time before we leave this, degrees of freedom mean controllable parameters, meaning how much you mix of each component, the temperature of the situation, the pressure of the situation, maybe even the volume that they occupy. If they happen to be in a gas phase, that can be controllable as well. And so those are our degrees of freedom. Components are how many things we are mixing, and phases are something to do with the states of matter, but we have to recognize in certain states you can have multiple phases, as we will see. Now, again, components count how many things you're putting into the mixture. That's fairly straightforward. But let's be clear about what we mean by phases. Notice I show a picture of the allotropes of carbon. There are actually 4 common allotropes of carbon which constitute 4 different phases in which carbon can exist in the solid state. So that's kind of the meaning of what we're going on. Carbon can be diamond, or it can be in graphite sheets, it can be in fullerenes, or it could be amorphous, which we more commonly refer to as soot. Very often liquids can be multi-phase liquids. Now, of course, when you have a multi-phase, any pure liquid is a single phase. So pure liquids are single-phase liquids because they mix homogeneously internally when they're one component liquids. Gases are single-phase always. All gases are single phases. We don't have separation of the gas components into different regimes. Now, what I'm showing here, of course, is a mixture of oil and vinegar, and really, if you want to get technical, it's acetic acid, water, and some oil. And the acetic acid and water are miscible. They separate into one component, and the oil goes into another component. Typically, the oil is less dense than the acetic acid water mixture. The oil floats on the top of the acetic acid water mixture, and then below that we have the acetic acid and water, and maybe some spices and things that make it look the color that you see there, but that's more dense liquid, and that phase of the liquid state separates from the phase of the liquid state of the oil. Now, technically, there's going to be a little bit of oil dissolved in the liquid phase water part. There's going to be a little bit of water dissolved in the oil phase above it, but this is an example of a two-phase liquid. Now, this is probably most correctly a three-component, two-phase liquid. The three components would be acetic acid, water, and some oil, whichever that happens to be, olive oil or canola oil, whatever I happen to use. So let's be clear when we're making these definitions. It's going to be important that we can differentiate things of this type, particularly now as we go to find how many degrees of freedom are going to be possessed in these situations. Let's look at the appearance of a single component or pure substance phase diagram. And in particular, let's make it very simple. Let's make sure that this pure component only has one solid and one, well, it can only have one liquid phase. Now, why could it only have one liquid phase? Anytime you mix a pure liquid, there is only one phase, always. One component can only be a one-phase liquid. Why? Because the intermolecular forces are such that one component homogeneously mixes among itself. But a one component sample can have multiple solid phases, multiple, depending on how the solid particles pack relative to one another. Take, for example, what I showed on the previous slide. Carbon can exist in the diamond phase, it can exist in the fullerene phase, it can exist in the graphite phase, or it can exist in the amorphous solid phase. All those are different than one another and have to be treated individually. So if this was a multi-phase solid, I would have different regimes in this gray area I'm showing for the solid. So I'm pretending here I have a single solid phase. That state is a single phase. The liquid is always, for a pure substance, one phase. Gas is always one phase for a pure substance. Now notice I'm showing above that in the right-hand corner something I'm calling a supercritical fluid. Fluid means is a special case of not really gas or liquid, but actually gases or liquids can both be classified as fluids. The supercritical fluid has some bizarre properties that I will try to explain on an upcoming slide. Let's forget the idea of the supercritical region right now and just notice that I have a line separating the solid state from the liquid state. I have a line separating the solid state from the gas state, and I have a section of a line separating the liquid state from the gas state. So these are what we call the phase boundaries. The line between the solid and liquid is the solid-liquid phase boundary. The line between the solid and the gas is the solid-gas phase boundary. The line between the solid and the liquid is the liquid and the gas is the liquid-gas phase boundary. Now notice this is a P versus T plot. If I were to look at the graphs below and I slide across a pressure of 1 atmosphere, go constant 1 atmosphere, and increase the pressure, I will notice that the equilibrium intersection at 1 atmosphere of the liquid gas phase boundary is at 273 Kelvin. That should make sense because when the pressure above the liquid and gas is, or the liquid is 1 atmosphere, then the temperature that that gas is exerting is 273 Kelvin. The vapor pressure of a liquid is at, the melting point, of the liquid is at 273, so that's when it has a vapor pressure of 1. So the ice melts at 0 degrees C, corresponding to when it is at 1 atmosphere pressure. That's where the ice will melt. Notice if you go to different pressures, the ice will melt at different temperatures, according to what we talked about before. Now let's slide to the second intersection point at 373 Kelvin. That also is along the 1 atmosphere line. That's where we see the transition from the liquid to the gas. The intersection or the equilibrium between the vapor and the vapor pressure that gas will exert at that particular temperature is going to equal the downward push of the atmosphere at the normal boiling point of 373 Kelvin. So we can look at the points where this occurs. We can also look at the supercritical temperature of the gas. Now that occurs at the temperature you see out there at the end, but it doesn't occur at a pressure of 1 atmosphere. Notice the pressure has to be way greater to reach the supercritical point of this water sample. Now, interestingly, for the carbon dioxide, notice if I go to 1 atmosphere, there's no intersection between the liquid and vapor phase. There's just an intersection at 1 atmosphere between the solid and vapor phase. And that turns out to be at 195 Kelvin. That is the temperature at which carbon dioxide changes at atmospheric pressure directly from a solid to a gas. So that's the sublimation temperature under normal atmospheric conditions for CO2. Notice if you put the CO2 at different pressures, you would change that sublimation temperature, because the 195 wouldn't be the point of intersection at, say, 2 atmospheres of pressure. So you'd have to have a different sublimation temperature if the CO2 is subjected to 2 atmospheres pressure.